Welcome to the second part of our compass series. This time we'll focus on the errors caused by magnetic dip. But first, let's take a closer look at the structure of the compass and unravel the mystery of its backward rotation. You probably already noticed that the old whiskey compass on your glare shield seems to be turning backwards. Like when you make a left turn from north, the heading indicator shows a turn to the west, the compass turns to the other side. Yet, magically, they end up agreeing with each other. Ever wondered why? Let's unravel this mystery. On a heading indicator, we get our heading information from the upper half of the compass card. But that upper half is hidden on the back of the compass, so we can't see it from the pilot's seat. What we see instead is the lower half of the card. Watch closely as the compass card rotates. Guess what? Even though it's spinning in one direction, the upper and lower halves move in opposite directions. That's why your compass seems to be turning backward. And no, it's not because the card is inverted. Though it is indeed inverted, but that's just for readability. Unlike the heading indicator, the compass card doesn't actually rotate as the airplane changes heading. Instead, it's the viewing window that moves around the compass. This happens because the magnet inside the compass case always points to the magnetic poles, or, you could say, it always aligns with the magnetic flux lines. So, the magnet rotates when the airplane's relative location to the magnetic poles changes. A mere change of heading does not move the magnet. However, from the pilot's perspective, it may feel like the compass card is rotating because the pilot is moving with the airplane, making the compass case appear stationary. But at the end of the day, it doesn't matter who's doing the dance, just remember, the numbers go up for a right turn and down for a left turn, no matter where you're starting from. Earth is like a giant magnet surrounded by magnetic fields. The magnetic flux lines enter the Earth's North Pole and exit from the South Pole. Surprise, surprise, what we commonly call the magnetic North Pole is actually the Earth's magnetic South Pole, and vice versa. This is because like poles repel each other, while opposite poles attract. So, technically, Earth's North Pole should be called the north-seeking pole, because it attracts the North Pole of other magnets. To keep things simple, though, we'll stick to calling them the magnetic North Pole and South Pole in the conventional way. As you can see, the magnetic flux lines are not always parallel to Earth's surface. The angle formed between the magnetic flux lines and the Earth's surface, or any horizontal plane parallel to the Earth's surface, is called the dip angle. At the magnetic equator, the magnetic flux line is parallel to the Earth's surface, so there is no dip. As you move towards the North Pole, the magnetic flux lines become nearly vertical. If a magnetic needle free to rotate in any direction is placed here, it will tilt downward, indicating a positive dip angle. Near the South Pole, the magnetic needle tilts upward. This magnetic dip is the culprit causing the compass turning and acceleration errors. To minimize the effect of the vertical pull of the magnetic field, the compass is designed to have its center of gravity located directly below its pivot point. This configuration increases horizontal stability. However, as the airplane approaches either magnetic pole, the vertical force becomes strong enough to tilt the magnet. The counterweight on the upside causes the center of gravity to appear to move away from the pivot point. This misalignment disrupts the equilibrium of forces, leading to compass errors. In the northern hemisphere, when an airplane accelerates from a west or east heading level flight, inertia resists the forward motion, pulling the compass's apparent center of gravity in the opposite direction of the airplane's motion. This causes the compass card to swing and falsely indicates a turn to the north. When the airplane slows down, the forces reverse, causing the compass to falsely indicate a southerly turn. However, this error does not happen when accelerating or decelerating from a north or south heading because the direction of inertia aligns with the pivot point and center of gravity, resulting in no net effect. Overall, the error is minimized when flying north-south and maximized when flying east-west. In the southern hemisphere, the apparent center of gravity is located on the opposite end of the magnet, consequently, the effect is flipped. Remember, these errors occur whenever the airplane accelerates or decelerates from an east or west heading, whether in the air or on the ground. We know it's the horizontal lift resulting from the airplane's bank that makes it turn. When the turn is coordinated, the inward horizontal lift is counterbalanced by outward centrifugal force. This works like a charm when the center of gravity and pivoting point are perfectly aligned. However, when the airplane banks, the compass joins in on the action, tilting away from being parallel to the horizon. This change in orientation, together with magnetic dip, shakes up the dynamics of forces. Without diving into the intricacies of physics, let's focus on the overall effect and resulting errors. In the northern hemisphere, when turning from a north heading, the outward force acts on the apparent center of gravity, pulling the magnet's tail to the outside. This causes the compass to show a turn in the opposite direction and lag behind the actual turn. Therefore, you should stop the turn before reaching the intended heading. No matter if you turn left or right, as long as you're turning from north, the compass lags. Always undershoots north. Heading south, the viewing window moves to the upper half of the compass card. Remember how the upper and lower halves of the compass card appear to move in opposite directions? Although the force acts the same as when heading north, the effect is different. This time, the compass leads the turn, so you'll need to stop the turn after reaching the desired heading. There is no error when heading west or east because the forces acting on the compass are aligned with the pivot point and the center of gravity. Thus does not cause it to lag or lead. In the southern hemisphere, the apparent center of gravity is located at the north end of the magnet, and the effect is reversed. Meaning you should overshoot the turn from north heading and undershoot from south heading. The effect and correction are opposite in the two hemispheres, but the magnitude is the same. It's 15 degrees plus half the degrees of latitude. Ignore the negative sign for south latitude. If math isn't your thing, 30 degrees is your magic number. It works for most cases. Keep in mind, turning errors result from magnetic dip and the aircraft's bank. Therefore, this error does not occur when the airplane is taxiing on the ground. Alright, that's a wrap on the magnetic compass. Next up, we're moving on to the flight computer and navigation terminologies. We're having a showdown between the magnetic family and the true family. Stay tuned.